Hello everyone, welcome to the course Electromagnetic Waves and Transmission Lines. I am Srikar, working as an assistant professor at Institute of Aeronautical Engineering, Hyderabad. And today we are going to discuss electromagnetic waves and transmission lines and some basic concepts of vector algebra. And without any delay, let's look at the definition of electromagnetics. And it is the study of interaction of fields which are generated by time-varying charge distributions and currents. Okay, if you look at the definition properly, there are many terms like fields and charge distributions, okay, which cannot be understood by a student at this moment because we don't know what a field is and we don't know how these charge distributions, time varying charge distributions and currents are responsible for generating electric and magnetic fields. And the next question is, how do they interact each other? How do electric and magnetic fields interact each other? So in order to answer all these questions, one has to study electromagnetic course, okay? And many of us have studied circuit theory, right, in your previous semester. And you might have all been exposed to several kinds of circuits, couplers, filters, etc., right? And the question one can generally ask is, why should one study this electromagnetic course? Isn't circuit theory enough to understand the concepts whatever are present in electrical engineering and electronics and communication engineering? And in the next few minutes, we will look at all these things in a great detail and how the circuit theory fails to answer questions which can be answered by electromagnetic theory. Because in certain situations, this circuit theory fails to predict the correct solution. Okay, let's do some exercise before we start this subject. I have a voltage source like this. And I have wires like this. Let's consider that these wires are ideal and these wires are very long. Okay. And the question in front of you is, if the circuit is closed, if the switch is closed, at t is equal to 0, what will happen? So this is the question. If the switch is closed at t is equal to 0, what will happen? So if I ask this question to people, they can come up with several answers. And one of those answers is, nothing will happen. Nothing will happen. And the second answer would be, current will flow for a short time. And the next one is, one may say that the question is not properly told because length and shape of the wire are not told properly. Outcome depends on the length and shape of the wire. And the next answer could be, outcome depends on the frequency of the source. The doubt one may get is, do these things really matter to answer this question? Let's do some exercise before this. Let's consider that I have a circuit like this. Okay. If the switch is closed at t is equal to 0, then what will happen? It will be like this. So, from our circuit theory knowledge, we can say that whatever voltage that is present across the input terminals will appear at the output terminals, right? Because in circuit theory, the length of the wire and shape of the wire do not really matter to us, because no matter how long the length of the wire is and no matter how the shape of the wire is, the output will be same as the input for this particular circuit. So this is one answer. And the next one is, if I bend some portion of a wire, some portion of this wire like this, okay, and if I connect a resistor in this fashion, then what will be the output across this resistor? If you see this one properly, the circuit is open before t is equal to 0. So when after t is equal to 0, the circuit will be closed, okay? And for a circuit guy who comes from a circuit background, whatever voltage appears at this point will appear here as well, because for him the length of the wire and the shape of the wire do not really matter, right? And if you solve the circuit properly, then suppose this is the voltage of the source. As we keep increasing the voltage of the source, and this wire causes the voltage drop across the resistor, to 0. And this wire causes the voltage drop across the resistor to 0. So this is something which is really unexpected, right? Because, you know, this bent portion of the wire, it acts as an inductor at low frequencies. And the same bent portion of the wire, it acts as a transmission line at high frequencies. And the question that comes again is, what is inductor? And how do we calculate that inductor? Actually, inductor is actually developed from electromagnetic theory. It is not developed from circuit theory. So to answer all these questions like what is inductor and how do we calculate inductor, one must study this course, electromagnetics and transmission lines. Okay. So here we know that the output will not be same as the input at the output will not be the same as the input voltage. It is almost 0 due to this bent wire. Okay. And let's do other exercise. I have a voltage source like this. If I cut some portion of the wire and connect those wires to large metal surfaces, okay. If I cut some portion of the wire and connect those wires to large metal surfaces, then what will happen? And we know that this particular situation is exactly that of a capacitor, okay. And if you see if you see the circuit properly, after t is equal to 0, the circuit is closed, okay. So actually there is some discontinuity between these plates, because there is no wire present between these two plates. However, current still flows in the circuit from this end to this end. So whatever current that appears here after the switch is closed, the same current will appear. The same current will appear here as well. But still there is some discontinuity between these two plates. Okay. So what happens actually in between these two plates? And this one, and the answer to this question cannot be obtained from circuit theory. And electromagnetics tells us what happens actually in between these metal plates. Okay. So what current that flows exactly in between these metal plates can be told by electromagnetic theory. So here we know that this one is nothing but a capacitor. Okay. And the question that will come automatically now is, how do we calculate this capacitance? How do we calculate the capacitance of this capacitor? To answer these questions, one must study this course electromagnetics. Okay, because the electromagnetics is a course which deals with the currents that flow in between these metal plates. There is something called displacement current that flow in between these metal plates, and here we have conduction current which generally exists in wires, and here we have displacement current which is generally present in between those plates. So you may not be able to understand what this displacement current is at this moment, but in the later sessions of this course we will study all those things in detail. Okay, so until now we have seen inductor, capacitor. Okay, and actually the concepts such as inductor and capacitor are developed from electromagnetic theory, and electromagnetic theory tells us how to calculate inductance and capacitance's value, right? Okay. Let's just know the solution of the first circuit which I have shown already. See, in our first circuit, it is told that switch is open before t is equal to 0. After t is equal to 0, the switch will be closed. So for a circuit guy, no current will flow in the circuit, and whatever voltage is present at the input will appear at the output as well. But if you connect these two terminals to a oscilloscope, and if we consider that the voltage waveform looks something like this. Okay, looks something like this, where at t is equal to 0 we have maximum value, right? And on oscilloscope, we will see a waveform like this. Okay, and if you observe properly, this maxima occurs at some t is equal to capital T. This maxima does not occur at t is equal to 0 on oscilloscope. So the input waveform experiences some delay after passing through this, after the current passes through these wires, right? So circuit theory does not incorporate all these things. Circuit theory cannot predict all these things, right? For a circuit theory guy, the output of input and output are same. The outputs of input and output are same. For electromagnetic guy, the output is a delayed version of input. Okay, if this is t, this is something like v of t minus t. Okay, and this t is exactly equal to L by V. L is nothing but the length of the wire, and v is nothing but the phase velocity of the wave. Okay, v is nothing but the phase velocity of the wave, and the term phase velocity will be discussed in later sessions of this course. And just keep it in mind that there is something called phase velocity, which is responsible for this delay. And if the length of the wire is large, then the wave will experience more delay, right? So what we understand from this circuit is the voltages and currents at any point on the wire are not just scalar variables; they are rather waveforms. So what we have thought about voltages and currents from circuit theory, they are not actually scalar variables; they are waveforms. And if I want to know the current at this point, okay, if I consider this is z-axis, then I of z comma t is nothing but I naught into cos of beta t minus omega z. So this is the delay or phase shift, and this one varies from point to point. And this phase shift is a significant fraction of 360 degrees. It's a significant fraction of 360 degrees, especially at high frequencies. And this beta is called as phase constant. Mathematically, this beta is nothing but 2 pi by lambda, where lambda is the wavelength of the wave. Okay, and v is equal to phase velocity is equal to omega by beta, which is equal to 2 pi f by beta. This f is the frequency of the source, right? And you will study about all these things like phase constant, okay, and phase velocity in detail in this course. So what we understand now is the wire is just not a wire; it is something more than a wire. Because of this, when we connect this input and load with a wire which is long enough, then the output is a delayed version of the input. Okay, circuit theory doesn't tell all these things actually. Okay, because circuit theory does not incorporate all these things. It doesn't take all these things into account. So we understand that some delay is there between output and input when they are connected by long pair of wires. So the question one may ask is, do these delays really matter? The answer is they matter a lot, because there are some computing devices like laptops, tablets, mobiles. They contain millions and billions of gates, logic gates, and these logic gates have switching times, right? These logic gates have switching times. These logic gates have switching times, right? Let's consider that the logic gate has a switching time in hundreds of picoseconds. If I connect two logic gates with transmission line, if I connect these two logic gates with this transmission line, let's assume that the delay caused by this transmission line is 200 picoseconds. Okay, so let's assume that after 100 seconds it switches from low to high. After 100 picoseconds, the output at this point switches from low to high. The similar waveform cannot appear here after 100 seconds, because there is some delay present due to this interconnect. There is some delay which is present due to this interconnect, right? So that's why these delays are very important. If you do not consider all these delays, you will get some inconsistent results. You may not get the desired output. So that's why one has to take care of all these things properly. If you are designing some high frequency RF circuits, okay, and if you are designing a circuit which consists of many logic gates, we should take all these things into account, right? Suppose if the input waveform here is like this, if the input waveform at these two terminals is like this, okay, this is 0.95 nanoseconds, 1 nanosecond, and this one is 10 nanosecond and 10.9. So to switch from low to high, it takes 0.5 nanoseconds, and to switch from high to low, it takes 0.5 nanoseconds, okay. And if I see the output at this point, at these two terminals, let's assume that I have square waveform as output. It should be something like this, right? But the actual output, if we take all these delays into account, then the actual output will be like this. You can see the ringing effect. You can see the ringing effect where we have peak overshoot and peak undershoot. And these electromagnetics and transmission lines predict these outputs properly because they take all these delays into account. Okay, so that's why the output at these two terminals cannot be square waveform, exact square waveform. It looks something like this. Okay, and as I have already told you that this is an interconnect and this is a transmission line as well. Okay, and every transmission line is characterized by some parameters like characteristic impedance and time delay. We know that this pair of wires causes some delay. So there will be some time delay when I connect these two logic gates with these two wires, right? And every characteristic line has a parameter called characteristic impedance, which is one of the most important characteristics, right? And the question that comes automatically now is, what is characteristic impedance and how do we calculate this characteristic impedance? Okay, so all of you might have known the definition. Impedance is nothing but voltage divided by current. Okay, this is a general definition. Everyone knows about this, right? So for this transmission line, what is voltage and what is current? Especially when we deals with high frequencies, this voltage is something which can be accurately defined in terms of electric fields, and this current is something which can be accurately defined in terms of magnetic fields. So now I can write Z is nothing but E by H. E by H, right? Because if I exit a transmission line with a voltage V, there will be electric field like this. If I exit a transmission line with a current I, there will be magnetic field like this. So I can relate this voltage to electric field here, and I can relate this current to magnetic field here. From this, I can get impedance. So as I told earlier, the terms like resistance, inductance, capacitance, they are actually developed from electromagnetic theory. They are not developed from circuit theory. They are actually developed from electromagnetic theory. And electromagnetic tells us things like how we calculate those resistances, inductances, and capacitances. So, if anyone wants to understand what these electric and magnetic fields are, then they have to study this course. Unless and until you study this course, we cannot understand what electric field is and what a magnetic field is. So, let's just summarize whatever we have studied till now. A wire is not just a wire, it is something more than a wire, because that wire causes some delay, which is very crucial when we consider when we design high speed digital circuits which have short switching times, right? And normal circuit theory does not consider all these things, whereas the electromagnetic theory considers all these things and predict the output properly. So this is the brief introduction of this electromagnetics. Okay, and from this you know what the importance of this course is. Okay, so after knowing the importance of this course, one should know the applications of this course as well. And if you see electromagnetic principles, electromagnetic fields, and electromagnetic devices, everything has some application. Okay, these electromagnetic principles find applications in various disciplines such as microwaves, antennas, electric machines, satellite communications, bioelectromagnetics, plasmas, nuclear research, fiber optics, electromagnetic interference and compatibility, electromechanical energy conversion, radar metrology, and remote sensing. And I am not going to explain how these principles are exactly useful in these applications. Just keep it in mind that these electromagnetic principles find applications in many disciplines. Okay. Similarly, electromagnetic fields and there are some electromagnetic devices like transformers, electric relays, radio, TV, telephones, electric motors, transmission lines, waveguides, antennas, optical fibers, radars, and lasers. So all these devices are called as electromagnetic devices because they work on the principles of electromagnetic theory. Okay, so unless and until you study this course, electromagnetic theory, and transmission lines, you cannot design any of these devices. So one must have thorough knowledge about the laws and principles of electromagnetics to design these kind of devices. So after discussing the introduction of electromagnetic waves and transmission lines, I would like to discuss vector algebra. In vector algebra, we are going to use a mathematical tool, vector analysis, which is the best tool to understand all the concepts in this course. So, whatever the concepts are present in this course can be conveniently expressed and understood and easily understood by using this mathematical tool. So, one needs to study, one needs to understand this vector analysis in order to understand the concepts in this course. So, if you take any quantity, any physical quantity, the physical quantity can be either a scalar or vector. Okay. So when can we say that the physical quantity is a scalar? If the quantity with the physical quantity has only magnitude, then we can say that it's a scalar quantity. And examples for this scalar quantity are time, mass, distance, temperature, entropy, electric potential, and population. Okay. So why are these quantities called as scalars? Because they are just numbers. They have just magnitude. They don't have any direction. Let's discuss about another quantity, vector quantity. If you see vector quantity, it has both magnitude and direction. Okay. And typical examples for these vector quantities are velocity, force, displacement, electric field intensity. This term might be new to you, electric field intensity. Actually, this term is in this course, electric field intensity. And you might have come across these terms like velocity, force, and displacement. And I hope that you know that these quantities are generally vectors. Okay. And there is another class of physical quantity called tensors, which is a special case of the scalars and vectors. Okay. And in this course, we are not much concerned about these tensors. Okay. We are only concerned about scalars, and in this course, we are not concerned about these tensors. We are only concerned about scalars and vectors. So let's look at these things in detail. So what is a scalar quantity? As I told you, it has, if a quantity which has only magnitude, then that quantity can be called as a scalar quantity. See temperature. Let's take temperature. If you see temperature, it is just a number, 30 degrees centigrade, 40 degrees centigrade, or 50 degrees centigrade. Okay, it is just a number. It does not have any direction. Okay, and if you take velocity of raindrops, if you take velocity of raindrops, if you take velocity of raindrops, if you take any raindrop, it has some velocity, it has some velocity and direction. It has some velocity and direction when it is in air, right? So this velocity of a raindrop, which is a physical quantity, is an example of vector. And this temperature is an example of scalar. Similarly, population is also just a number. It does not have any direction. So that is also a scalar quantity. Okay. Gravitational force, it's a vector because gravitational force always in downward direction on a body, right? And this one has some magnitude and direction. So gravitational force is also always considered as a vector. Okay. Let's see the notation of scalar and vector. And if I want to denote a scalar quantity, suppose let's say that a physical quantity called A is there. Okay. If I say this is a scalar quantity, I should just represent it like this, A. If I want to represent this one as a vector quantity, then I should make this letter bold. Otherwise, I can represent the same vector quantity in this fashion as well. A with an arrow over its head. This is a vector quantity and this is a scalar quantity. Okay. While I was discussing the definition of electromagnetics, we came across this term field. We came across this term called field. So, what does this field represent? What is a field? So, in simple terms, a field is nothing but a function which specifies a particular quantity everywhere in the region. It is nothing but a function. It is nothing but a function which specifies a particular quantity everywhere in a region. If the chosen quantity, if the chosen quantity is scalar, then we can say that the field is a scalar field. If the chosen quantity is vector, then we can say that the chosen quantity is a vector field. Okay. So if the quantity is scalar, the field associated with that quantity is scalar. So if the quantity is scalar, suppose if temperature is the quantity which is chosen, we know the temperature is a scalar quantity. So the field associated with the temperature is also a scalar field, right? Similarly, we know that velocity of a raindrop is a vector quantity, and the field associated with that velocity of the raindrop is a vector field. So typical examples of scalar field are temperature distribution in a building, or temperature distribution in a state, temperature distribution in a country, or temperature distribution in world. Sound intensity in a theater, because in theater also the sound intensity cannot be same at all points. Sometimes the sound intensity varies from position to position. And electric potential in a region, refractive index of a stratified medium. And these terms might be new to you because you have not studied this course till now. And typical examples of vector field are gravitational force on a body in space and velocity of raindrops in the atmosphere, right? See, let's take Hyderabad as an example. Let's consider that today's temperature in Hyderabad is 45 degrees, 40 degrees centigrade. And in other place, Warangal, the temperature is 43 degrees centigrade. In other place, Ramagundam, the temperature is 48 degrees centigrade. Let's consider that this is a map of Telangana. and Hyderabad is somewhere here. Temperature is 40 degrees centigrade. And Warangal, the temperature is 43 degrees centigrade. It is represented with some bigger dot. Okay. And at Ramagundam, it is 48 degrees centigrade. So this temperature distribution is an example of scalar field, because every point has some coordinates. At Hyderabad, the coordinates are some x1, y1, z1. At Warangal, the coordinates are x2, y2, and z2. At this Ramagundam, the coordinates are x3, y3, and z3. As I told you, a field is a function which is represented with the coordinates x, y, and z. If the chosen coordinate system is Cartesian coordinate system, then the coordinates are x, y, and z. If the chosen coordinate system is cylindrical coordinate system, then the coordinates will be rho, phi, z. If the chosen coordinate system is spherical coordinate system, then the coordinates are r, theta, and psi. Okay. So this temperature distribution is a typical example of scalar field. Let's see how a vector field look like. Okay. Let's consider Hyderabad example. Hyderabad as an example again. Let's consider that it's raining in Hyderabad. Okay. And the raindrops are exactly coming perpendicular to the ground. Whereas in Warangal, the raindrops are coming in this fashion. Whereas in Ramagundam, the raindrops are coming in this fashion. This happens generally due to wind or some other distributions in the atmosphere. When there is wind or some other distributions in the atmosphere, you cannot expect raindrops exactly coming perpendicular to ground. Okay, so sometimes the raindrops can be in this fashion as well. So if you see this example properly, if you take any raindrop, it has some velocity while it is in air and some direction. Here the direction is exactly perpendicular to the ground and towards the ground. And here it is not exactly perpendicular to the ground. It is inclined at an angle theta 1. In this case, it is inclined at an angle theta 2. And here also, if you take any raindrop, it has some velocity and direction. And here also, if you take any raindrop, it has a velocity and direction. So in Hyderabad, the vector, the velocity of the raindrop is in this fashion. In Warangal, it is in this fashion. Whereas in Ramagundam, it is in this fashion. If I consider that this is the map of Telangana, then vector, then the velocity of the raindrop in Hyderabad is like this. Whereas in Warangal, it is like this. Whereas in Ramagundam, it is like this. And this particular distribution is an example of vector field. Because at any point at any place in Telangana, we can define the velocity of a vector with some magnitude and direction. So that's why it's a vector field. Let's see one more example. You can see here, this is a room. Let's consider that this box is a room, okay? And the temperature varies in this room according to this equation. T is equal to x square plus yz. So if I plot temperature, if I find out temperature at each and every point in room, the temperature distribution looks like this. Because at high values of x, y, and z, the temperature value is high. So that's why it is represented with some thick color. And this part is not represented in thick color, right? Represented by thick color. So temperature at this place is much lower compared to the temperature at this place. Okay, and this this temperature distribution is an example of scalar field. Suppose if there is an electric field, in this room, like this, okay, which varies according to this equation, and the electric field, as I told you, this electric field is a vector quantity. That's why it has a magnitude and direction. Okay. If I plot electric field at each and every point in this room, then it would appear like this. Okay. You can see there are several vectors which has a magnitude and direction. At specific point P1, 2, 3, the direction is like this. Okay. The direction is like this. So this one is an example of vector field, whereas this one is an example of scalar field. So we know that a vector has a magnitude and direction, right? Suppose if I have a vector A, okay, it has a magnitude and direction, right? If I want to find a vector which has magnitude 1 along the direction of A, suppose I have a vector like this, which is A. If I want to find a vector along the direction of A, which has magnitude 1, then what should I do? First of all, I should find out the magnitude of A, this vector A. Then I should divide this vector with its magnitude to get this vector. This is A. So this one is unit vector along the direction of vector A. See, suppose if the magnitude of this one is 5, okay, to make this quantity, to make the magnitude of this one 1, then what should I do? I should divide this vector by its magnitude. So 5 divided by 5 gives 1. So A by mod A. So A is nothing but unit vector along A, which is nothing but A bar by mod A bar. See, if you see if I want to find out the magnitude of this one, then what will happen? Mod of A bar by mod of A bar. So mod of A bar is 5. Mod of 5 is also 5. So 5 by 5 is 1. So any vector divided by its magnitude gives us a unit vector along the direction of that vector. Okay. So a vector A in Cartesian coordinate system or rectangular coordinate system. In rectangular coordinate system, we have 3 dimensions: x, y, and z. Okay. And any vector can be represented in this fashion: ax plus ay plus az. So any vector can be represented in this fashion. And this one is a component of vector along this direction. And this one is the component of vector A along this direction. This one is the component of vector A along this direction. And this one is the component of vector A along this direction. Okay. See, if you see this properly, this one is x, and this one is y, and this one is z. Let's consider that there is a point here. And if I draw a vector which has its tail at origin and head at this point P. Okay. Let's consider that this A is this one, ax plus ay plus az. So this vector is a combination of 3 vectors. So this is one vector, this is another vector, and this one is another vector, right? So ax means it is a unit vector along x-axis. So ax is generally this one, unit vector along this axis, along this x-axis. So ax is this one. Ax is this one. Ay is this one. Ay multiplied with some magnitude means it will be like this. Okay. This is ay. Right. This is az. Az is this one. So AZ into AZ, let's assume that AZ is something greater than 1. So this is AZ into AZ. Okay. Now how can I get vector A from these three vectors? If I add these two vectors, so this is one vector and this is one vector. The resultant of these two vectors will be like this. The resultant of these two vectors will be like this. I will tell you why the resultant will be like this. So okay. So if I have one vector like this and the other vector like this, what is the resultant of these two vectors? A plus B is a vector which has its tail at A and head at B. So my first vector is in this fashion and second vector is in this fashion. So I can take a vector, similar vector Ax into Ax here as well. So can I have two same vectors at two different places? Of course I can have two same vectors at two different places because the velocity of the raindrops can be same at two different places with same direction. Okay, so that's why I can draw a vector which is parallel to this vector and located at some distance from this vector. Okay, see this, if I consider this one as the first vector and this one as the second vector, this one as the first vector and this one as the second vector, the resultant vector will be like this, Then what is the other vector? Az into Az. So Az into Az is a vector which is along z direction. Now I can take a vector which is parallel to Az into Az, okay, and has magnitude which is exactly equal to Az. So this is the vector. If I want to find out the resultant of these two vectors, this vector and this vector, this is the resultant of these two vectors. So A is nothing but Ax plus Ay plus Az. So any vector can be decomposed into three vectors along x, y and z axis. As I have already told you, Ax is the component of vector A along x-axis and Ay is the component of vector A along y-axis. Az is the component of vector A along z-axis. You can see here. This is the component of vector A along x-axis and this is the component of vector A along y-axis and this is the component of vector A along z-axis. So this one is Az actually, this one is also Az, parallel vectors. These two are parallel vectors. So Ax is the component of vector A along x-axis, Ay is the component of vector A along y-axis and Az is the component of vector A along z-axis. So how do we calculate the magnitude of the vector? So if I have a vector like Ax plus Ay plus Az, then its magnitude can be easily calculated from this expression. Root of Ax square plus root of Ay square plus root of Az square. How can I calculate the unit vector along the vector A? It's nothing but vector divided by its magnitude gives us the unit vector along the direction of A. Okay, suppose if I have a vector like this A bar, and if I want to find a vector which has magnitude 1, if I want to find a unit vector along the direction of A, then what should I do? I should just simply divide that vector by its magnitude. So that is what is done here. So along the direction of this unit vector, So along this direction, I can define any vector, right, which has direction like this. So you know how to add two numbers and you know how to subtract one number from the other number. But here the quantities are not just numbers, here the quantities are vectors. Then how do we add two vectors? Suppose if I have vectors like this, A is equal to AX, AY, A is equal to AX plus AY plus AZ, and B is equal to BX, AX and BY, plus BZ, Then what is C? C can be found out from this equation. You just have to add the components of A and B along X direction to get the component of C along X direction, and add the components of A and B along Y direction to get the component of C along Y direction, and we have to add the components of A and B. We have to add the components of A and B along Z direction to find out the component of Z component of C, right? And similarly, you can subtract one vector from the other vector using this formula. See, as I told you, how to find out the resultant of two vectors. Suppose I have a vector like this, A, and I have a vector B like this. And this vector has its tail here, and this vector has its head here. If I see this vector has its head here, and this vector has its tail here. So what is the resultant of these two vectors? The resultant vector. What is the resultant of these two vectors? A bar plus B bar. It has its tail at the tail of the first vector and head at the head of the second vector. So this one is A bar plus B bar. Okay. Suppose if I have a vector A like this and vector B like this, then how to find out A bar plus B bar? Because the second vector's tail, the tail of B is not at the head of A, right? The tail of B is not at the head of A. Then what should I do? I should construct a vector which is exactly parallel to vector B and has its magnitude exactly equal to B and direction also in the direction of B. And the question is, can I construct a vector like this? Of course, we can construct a vector like this. Suppose this is origin, and this is 2, 0, and this is 0, 2. This vector is 2ay, and this vector is 2ax. If I consider a point which is 2, 2 here, if I consider a vector like this, which has its head here at this point and tail here, this vector is also 2ay, because this vector is like this, 2 minus 2 into ax plus 2 minus 0 into ay. So this is 2ay. So this vector is exactly same as this vector. This vector is exactly same as this vector. So I can construct a vector which is exactly same as this vector at different places. Okay. So this is first vector and this is our second vector. And the resultant vector will have its tail at A, at the tail of A, and head at the head of B. Okay. This is how we add two vectors. And how do we subtract one vector from other vector? Suppose this is a vector A and this is vector B. And how will be the direction of minus B? Exactly opposite to this one. Okay. And what will be the resultant of these two vectors? This one. Because I can construct a vector A in this fashion. Okay. Now this is first vector. And this is first vector which is minus B. And this one is second vector which is A. And B is equal to A bar plus of minus B. So which is equal to A bar minus B bar. Okay. Okay, let's end this session, and we are going to discuss about the rest of the things in algebra in the later session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.